Okay, we've got our 4 points. We've got the first point at 1, second point is 0.1, third point is area is 0.2 square meters, and at the end of the tube the area is 0.5 square meters. Going back up to the top, we've got the formulas now is linear interpolating between those 4 points, and we can, if we wanted to, we could get a plot of distance on the x-axis and area on the y-axis, insert a graph, scatter graph, and then we have area versus distance up to 100. Just stop that going to 120 by fixing it. So there's the area versus distance. I'll just get rid of that. The flow rate will take a value of initial value of 10, and this can be in cubic meters per second. The flow rate is a quantity. Typically in it's either a mass flow rate or a volume flow rate. Here we're assuming a volume flow rate. We want to keep it simple, and that's in meter cubed per second. The velocity then is calculated by dividing the flow rate, which is in meter cubed per second, by the area, which is in meter squared. The net result will be in meters per second. Meter cubed per second divided by meter squared is meters per second. The pressure change then, we need to use the formula, Bernoulli's equation. If the velocity is 10, then if you remember, if the velocity changes here half rho v squared, then the pressure has to be equal and opposite to that. So if the velocity goes up by half rho v squared, sorry, if the kinetic energy goes up by half rho v squared, then the pressure energy has to decrease by half rho v squared. So this formula then for pressure is simply equals minus 0.5 times the density of air, which is 1.2 kilograms per meter cubed, times the velocity squared. Use the up arrow for squaring, or for any power. Up arrow 2 is squaring. So we have a pressure drop then at the beginning of the pipe of 60 newtons per square meter. Now we've got the formulas in here. The quickest way to copy it down is just to highlight the whole lot, and that should, actually that doesn't copy down, make that 10. We don't want the flow rate increasing. The flow rate is constant. You'll have to try and think about that. Why is the flow rate constant? So now copy that down. I mean, we can copy them down one column at a time if you want, or you can copy the whole lot down. Let me just go back there. Shouldn't have done that. I was just seeing if the flow rate would stay constant. You've got to highlight 2 because we want the flow rate to be constant. Copy it all the way down to the bottom, and that's the answer. Just a quick check. I'm just checking here that the numbers are reasonable. We just decrease the number of decimal points. 2 decimal points is fine. And there we have it. We are now calculating the pressure. That's the pressure column. We have 60 newtons per square meter drop at the start of the pipe, and where it narrows, the pressure drop at the smallest cross section is a pressure drop of 6,000 newtons per square meter, and that is quite a pressure drop. By increasing the speed by a factor of 10, the velocity has gone up from 10 to 100 here. The pressure drop has gone from 60 to 6,000, and 6,000 newtons per square meter is effectively 600 kilograms per square meter. So that's like that's about 8 or 9 average people. It's the weight of 8 or 9 average people standing in a 1 meter square. So you can see the effect of increasing pressure is quite immense. Once you've got this table, then you finish the spreadsheet, and it's just a matter of getting some good plots out to show that you've got some sensible results. Distance, area, flow rate, distance, area, flow rate, velocity and pressure change. Let's have a go at plotting that as a scatter graph. And there we are. You can do things like putting 1 on a secondary axis. So it looks, if the scale of one is way different to the scale of another one, then just highlight that curve and move it to a second axis. Here's the secondary axis on the right hand side. The x-axis is going up to 120. We don't want that, so I right click on it, format data series. No, that didn't work. Format the axis. Format axis, here we are, and make the maximum 100. And that's it, job done. And that's the same as what we have in this graph here.